Okay, welcome everyone. We're going to do this in two parts, like Jen mentioned. This is the first part, sensor technology, fabrication, and testing. Is that sharing okay? There we go. Try.
Yep, that looks good.
I needed to click one more button. All right, so as I've tried to do in the past, I'm going to go through the steps in production order, hopefully a little more efficiently than last time. And I'm going to try and cover the testing details when they match up to the relevant production step. So I apologize in advance for the clutter. This seemed like a good way to do it until I was reviewing everything. That sometimes happens. So we'll begin with the sort of an overview of CCD and CMOS operation. This will be old stuff to all of you, of course, but I want to show some pictures in a way that gets us all on the same page. CCDs, as a reminder, don't operate in the same electrical way as the volts and amps that you're used to from the wall socket. It's much more like high school physics when you studied E fields and charge. The photoelectrically generated charge, which is in either the front or the back side of what you're looking at here on the right, is stored in potential wells that are created within the buried channel. The buried channel is this green region here that then propagates up into the image area. So this is in the upper left of this figure is where the image pixels are. And then you're looking at the last 4 pixels in the serial register. The darker blue is aluminum metal, and it's contacted to polysilicon at the squares. You can think of the squares as sort of like circuit board vias. And changing the voltages on the aluminum changes the voltages on the polysilicon, which in turn changes the field gradients in the channel. In this case, the buried channel is N-type silicon, but it doesn't always have to be. N-channel simply means that we collect we collect electrons rather than the absence of electrons. It also means that we collect those electrons in the channel under relatively positive gates. Then we systematically and cyclically control the voltages on the 3 phases, creating a moving series of waves that the electrons sort of surf their way toward the output node, which is just to the right of this summing well. Here is the output node. And that output node is the gate of the MOSFET, which is serves as a capacitor. So any charge that's put on that capacitor turns into a voltage on this gate that's proportional to the charge put on the capacitance and the capacitance. And then this output FET here buffers that with a gain of about 0.6. Contrast that with the CMOS device. A CMOS pixel's a lot more complex in design, so I'm sort of just showing the cartoon picture of what's going on here. The complex charge movement process doesn't happen in a CMOS device because each pixel has its own buffer output. This is much more like probing the capacitor with a voltmeter. So each pixel has its sort of voltmeter right here. It's probing the charge that's collected on the capacitance, which is actually just the photodiode, the parasitic capacitance of the photodiode. On the Hawaii NRG devices, the 4 blue diodes in the picture here above the D subnodes are on a separate Mercad telluride semiconductor die that's bump bonded to a silicon multiplexer. The die is not CMOS. It's a regular array of regular in the gridded sense of the word regular array of the PN diode junctions. The diode array defines the pixels, and the lithography used to produce it is key to the pixel uniformity. The 2 switches and the buffer in each pixel and the rest of the shift registers are on a silicon CMOS multiplexer. So in an NRG device, the CMOS is what you interact with, but the photodiode array is the ruler, if you will. The acronym CMOS sort of tells you how the device is made, whereas the acronym CCD tells you how it's operated. But I suppose you could make things differently and call it something different. Each of the colors in the CCD design that I showed represent a separate mask in the production process. We make those masks with an E-beam printer that has a resolution of about 10 nanometers. They cost about $5,000 to $10,000 a piece. That resolution has a direct correlation with the periodic flat field structure. This is an STA 1600 field, so a 10K field with, and then the next slide will show you without the resolution, the high resolution lithography masks. So this is the community sort of with Express. This was fed back directly into our production process. We didn't want periodic structure. You can see these vertical lines here. We didn't want that. Nobody wanted that to be imprinted on the data from the spectrograph. So we upped the resolution of the masks that were used to print the lithography. And this is what the final result was. So we didn't change anything else about the process other than the resolution of the masks used to print it. So we made, like I said, we made that switch for the 1600 for Express, and then applied that same technique to the 4850 and to a few other science devices that are used for millipixel level science. 4850 is used in Maroon X and KPF. The point here is that it's hard to change stuff once it's made, but you should definitely feed things back to us because we can sometimes make things better. So this is a horizontal slice through those two flat fields that I showed. The blue at the bottom was sort of the previous masks, and the red at the top is what we get with the higher resolution masks. The masked resolution problem is related to the stitching problem that you'll see on E2V devices and other, well, really anything that's produced from now going forward. Until lithography reached about a 1 micron feature size, it was printed with either direct contact or one-to-one imaging systems. Interestingly, those systems sometimes used an Offner relay system for the optics, and Ashley's going to talk about that later in the second part. Now that lithography is much smaller than the one-to-one systems are no longer made, and everyone has moved on to systems with huge reduction, which is usually about 5:1. So our 125 millimeter masks are now printed onto the silicon in 25 millimeter chunks. The consequence is that the masks are not large enough to create a large format CCD in one shot. Really any large image sensor in one shot. They could be, but there's no reason for a fab to make microprocessors that are 60 to 100 millimeters on the side. So the technology just hasn't evolved that way. So all of us who do large image sensors, including the IR guys, the Hasselblad camera guys, and the Leica photography guys, we're all stitching devices together at this point. Or we're switching to that like we are. So for newer CCD designs, our masks now contain one CCD design chopped into pieces representing different parts of the CCD. The serial, the output stage, the area, the edges, the pads, and we piece those together in the lithography problem. So, so this is what those reticles look like now. So you can see that we stitch these pieces together, and the image region here is then stitched together in a grid. And this is the 5100, which would be the newer generation of the 4850, but printed with stepper masks. And the reason I want to mention all of this is because we're going to start to see phase errors between the stitched image sections. And so it should be important for all manufacturers to document this reticle pattern in their data sheets and measure and report the phase errors that they see with the test data. So how do we measure that? I can really think of sort of 4 ways to do that: spot projection and reticle projection, which Ashley will talk about later. We can infer that possibly from the PRNU data, the flat fields, because charge is conserved. And then we can use a technique called fringe projection. So this is perhaps a little confusing. This is a 1600, so it's not produced with the stitched masks. But I wanted to use the technique to show what we could do in terms of fringe projection to measure the positions of these stitching errors. This is the Express 1600 CCD as imaged in Mike Shu's lab at JPL with a high resolution interferometer projecting fringes onto the sensor. So I'm going to zoom in on the green box here. So that's the full 10K pattern with overscan, parallel and serial overscan. We'll zoom in to a region. You can start to see the fringes, which are vertical lines here. I'll zoom in once again. So we have a very regular grid of sinusoids projected across the device. And the thought is that you could use this to measure really, really precisely the phase offset errors between those stitched regions. The intent here with Express was to actually measure the positions of the pixels individually, but it turns out to be that's quite hard with a window separating the CCD from the interferometer, because the dust on the window tends to project interference patterns on top of everything else that you're wanting to look at. But it's a good regular grid nonetheless. So wafers themselves start as either epitaxial or bulk silicon, depending on how thick we want the final device to be. Epitaxial simply means that it's a highly pure doped silicon that's grown on top of a less pure base wafer. We then etch that base wafer away. We could also start with very pure bulk silicon, which is what we do for anything thicker than about 50 microns. Typically, it's 150 to 10,000 ohm centimeter compared to CMOS, which would be the silicon multiplexer in a CMOS device or in your memory is more like 10 to 50 ohm centimeter. The cartoon picture is that the electric fields don't exist inside conductors. So the higher the resistivity of the silicon will have a higher field gradient and allow the thicker silicon to operate properly as a CCD. The thicker silicon allows for more red sensitive devices and reduces fringing and that kind of thing. Your phone's camera probably has an epi layer that's maybe 4 microns thick. Old astronomical CCDs were about 15. More recent devices are 30 to 50 microns thick. The thicker devices don't use epitaxial silicon. They use the 10 kilo ohm centimeter material, which is extremely hard to work with because it's so pure. The impurities, the dopants in the high resistivity silicon correspond to parts per trillion level of doping concentrations. I'm going to go back a slide. So we produce the epi. We then do the lithography on the top of the epi, the top side here, which we can call the front side. We then put gold or indium bump bonds on the pads, flip that over, squash it to a substrate which has the mating gold or indium bumps. The substrate's also made of silicon, and the purpose of that is simply to fan out the pads so that we can attach wire bonds to it. And then we underfill that gap between the CCD sensor and the substrate wafer with an epoxy. And so that's the ITL process. That's what you get with a 4850 or a 1600 or most of the devices that we've made over the last 20 years. A newer process, and this is similar to what a lot of other sensor manufacturers are doing, pretty much anything in your high-end phone that's got a backside sensor or in your camera that's got a backside sensor is going to be made this way. And we've done a lot of this as well. So the CCD starts as the same thing, but then it's planarized by spinning on glass onto the epi side and polishing that extremely, that's sort of atomically flat, if you will, and then that's flipped over and direct bonded to an equally highly polished handle wafer. And because both surfaces are atomically flat, they sort of contact bond, so there's no glue between these surfaces. Then you grind away the backside and passivate it with either chemisorption like we do in the dye thinned process, or with an MBE layer or ion beam implant, like boron implant. Then it's AR coated, but you have no way to access the bond pads, which are now attached to the handle wafer. So we do a back pad etch to uncover the bond pads and attach to the backside of we attach the wire bonds to the backside of the bond pads in these little troughs here. Another way to do that would be to create through silicon vias here and attach the bond wires to the underneath side. Both are fairly expensive processes to do one at a time, but it's significantly less expensive when you've got multiple die on a wafer. So we've also moved to larger wafers so that we can take advantage of this. The pad etch is proving to be, interestingly, the difficult step in all of this in terms of cosmetics. And then we dice and dice after the bonding and the thinning and the pad etch. Let's get that. Okay, this is analogous to what's done on the Hawaii NRG arrays. It's just called substrate removal there. So in the data sheets, when you see substrate removal, it's really a similar process to back thinning. The substrate's not silicon. In this case, it's a cadmium zinc telluride that's thick and handles sort of the mechanical aspects of producing the photodiode on the Mercadtel. It's then flipped and bump bonded on a per pixel basis to the silicon multiplexer underneath. And I wanted to show this because whereas on a CCD, you might have 100 pads, and where we put maybe 4 bumps on each pad, on an NRG device, you're going to see a bump per pixel. So a huge number of bumps. Okay, the anti-reflection coating, the AR coating is historically one of the more challenging in terms of yield parts of the production process. And I wanted to highlight this because it's where sort of the fringing starts. So why do we go into all that thick stuff? It's where we lose all of our money. It's the thinning stack up that results in the fringing patterns that we see on KPF and other instruments. The underlying mechanism of fringing is the interference within the absorptive thin film of the CCD thickness and the epoxy thickness. It manifests as a rapid periodic variation in the QE versus wavelength function. The fringe is related to the front and backside reflectance. So the better your anti-reflection coating, the lower your fringe, the better your front side, which is this intermediate layer. The better the darker that layer is, the less the fringing will be. It should be stable, but there's a big amplification term due to the refractive index and the thickness. So thicker silicon also reduces fringing and increases the red sensitivity. It's sort of like an etalon, but because silicon has a complex index of refraction, because it's absorbing light at the same time as it's transmitting light, it just works a little bit differently. The measurement of fringing is similar to when I do this in the lab, it's similar to what I do for QE, but it has I use the same setup, but with a much narrower bandwidth. That's because the coherence length of the light is dependent on the wavelength and the bandwidth and the index of refraction, because everything's done in immersion here. And so the narrower that bandwidth, the longer the coherence length of the light, and as that coherence light exceeds the thickness, or rather twice the thickness of the silicon, we start to see those fringes. So 30 micron episilicon requires something like a 2 nanometer spectral bandwidth to see the fringes. And you will see those fringes once you get to, like in the spectrographs where everything's much narrower than a nanometer, you're going to see fringes even in the thickest devices at the red cutoff, at least in silicon devices. You can also blur them out by fast focal ratios, and the effect is significantly reduced when you get below f1.4 on the camera. This is the machine that we use to characterize the coating performance and measure QE and measure fringing. I call it Chromoplex. It's an f5.5 system, about 1 meter long, with a bunch of very, very dark baffles within it. The illumination non-uniformity that this projects on the sensors is approaching the theoretical limit. That's very close to the theoretical limit, but well below 1%. across a 200 millimeter 8-inch wafer, which is much larger than anything that I put in front of it. It also scales with the intensity, also scales with Z as you'd expect. That's my time. Okay. Going a little slower than I want, so I'm going to skip ahead a little bit. Okay, so this is measuring the fringes on the KPF CCDs. This is, I think, the first KPF red CCD. We sample it at, for this image, I sampled it about 1/10 of a nanometer, but I'll usually sample a little bit more coarsely than that. And you can see sort of two fringing patterns going on. So I collect this data and then I measure it versus wavelength. You'll see a nice sinusoid, or rather a beat frequency pattern here with that corresponds to the two different fringe patterns that you're seeing. So the first one, the darker, higher contrasty one, is a 3.36 nanometer spacing, corresponding to about 253 waves throughout the thickness of the silicon, which, when you include the high index of refraction of silicon, corresponds to a thickness of about 30 microns, which is the design. The other fringe pattern took a little bit of investigation, but it corresponds to the epoxy layer gluing the silicon sensor to the handle wafer. We do a Fourier transform on that, and you can extract the information you need to figure out thicknesses and other things. Ashley's going to talk about that a little bit later. Finally, after we've made the devices, we package them on a substrate that can be Invar, aluminum. In this case, it's CE6. KPF and Maroon Expos use this 4850 package that we designed specifically for EPRV. It builds on a NUID, Express, and Virus experience, but it's a kind of a completely new concept with no intermediate cooling plate. And the idea is to drastically reduce the thermal time constant so that we can have better temperature control, but resulting from a tighter loop between the source and the sense. The source being the heater and the sense being the temperature sensor, both directly bonded in the package. And then we also, the other key factor here is we elastically couple the sensor to the outside world. So it's symmetric and thermal expansion, very stiff in XY positioning, and it minimizes the position in X, Y, and Z versus temperature relationship. Then after it's packaged, we put it in a test doer, put it on the Chromoplex system, and start collecting data. The first thing we do is collect a photon transfer curve that's used mainly to get to determine that everything's behaving and to get a gain that goes into the quantum efficiency calculations. This data is collected all at one time in a single frame. Archon's a flexible enough controller that I collect these big stacked flat field frames, and I can extract a photon transfer curve and a linearity curve and CTE data and read noise and signal, all from a single image. So this is the linearity data from the KPF. I want to say this is the KPF green CCD. And then the residual nonlinearity is plotted beneath that. This is the charge transfer efficiency that we get we get the charge transfer efficiency by looking at the first column of overscan after the last column of active in relation to the overscan mean. We can do that if the PTCs look good. Okay. And then we do the same thing with the parallel overscan to quantify the charge transfer efficiency in the parallel direction. This is usually significantly better than in the serial direction because everything's clocked much more slowly. And the fact that we're sort of 7 nines CTE here is one of the reasons that KPF can get away with using 2 output amplifiers, like Ashley will talk about a little bit later. The QE curve. That. Okay, so the last thing, or the next last thing I want to talk about before I run out of time, is how this charge transfer process works in the silicon. The electrons are held and moved throughout the channel epi interface at about 0.3 to 0.5 microns from the surface. So here's I've oriented this the way that we like to see CCDs as astronomers, with everything that we want to look at being up and light coming down onto the silicon. So we're looking, this is the back side, this is the front side where all the active stuff is, and this is a confusing plot, but it's from Jim's book, where distance is the vertical axis and voltage is the horizontal axis. And so charge is collected or produced photoelectrically here and drifts down into these potential wells that are created within the buried channel. We want to stay away from the surface because that's where all the traps are. So as you fill up this potential well, that changes the field, changes the shape of the field, and it can move charges toward the potential well. It can also uncover more traps that may exist. So you got to think of this channel as being a volume. And as you put charge on the pixels, it will change the part of that volume where the charge is and potentially uncover more traps. Charge transfer inefficiencies caused by several mechanisms. We usually measure it with EPR, which is this extended pixel edge response. So this is the overscan, serial overscan, the image areas to the left of the plot here. The overscan is fairly flat, except for this first pixel in the overscan. That's actual charge that's fallen on the overscan because it didn't get transferred. This is sort of a global phenomenon. It doesn't really capture the detail level of what's going on when you measure it this way, especially at high speed. So we typically will clock fast to move the charge to the output amplifier and then slow it down to read it out. Another way to measure EPR is to use iron 55. But that's sort of only, iron 55 decays with an X-ray photon. The X-ray photon produces a known number of electrons in a very tight group within a single pixel. But it's always the same number. So it's hard to characterize how the charge transfer efficiency is affected by the signal level. The principal mechanism to charge transfer inefficiency is low-level traps, especially at the output node. The output node's at one defined location. It's not accurate to divide. It's not an accurate characterization of that trap to be dividing that by the number of transfers, which is the method you use if you were trying to characterize CTE with the EPR response. So the CTI there is usually really bad because it affects every pixel, and it would manifest in the EPR response as being some low-level signal, but depending on where it is, it can have a bigger effect on all of the data. So we try to find traps another way, which we call charge pumping or shuffling, and it's fairly easy to find those traps that way. So what I'm doing here is I've taken a normal flat field that's fairly low level. This is a section of a single output of the 4850. Bend one in the serial direction, but then bend a lot in the parallel direction because I'm looking for traps only in the serial register. That's about a 200 millisecond exposure, pretty low level. I then read it out two ways. First, I read it out as a normal flat field. Then I do a second exposure. And while reading it out, I shuffle the charge left and right and user-determined amount of times. This causes the traps to sort of pump charge to the left or the right. A trap will tend to release charge at a different rate than it absorbs charge. And it will also do that in a different direction. So when you so there's the whole serial register. If I zoom in on just a section of that, you can see what's going on with the traps. I'm pumping charge left and right, and the trap will either release charge more slowly when it's moving in the left direction or in the right direction, but not equally in both cases. This causes charge to move and create these little characteristic p-sigma profiles that are very easy to find, and are fixed within the silicon. And we can characterize this as a function of signal level and a function of position. And I argue that those traps are sort of the root cause of the CTE that we see. The trap size is exacerbated at higher pixel rates. So when I run a faster pixel rate, I have to run a faster clock rate to transfer the charge. And so that's going to the left on the plot here because I'm plotting time rather than rate. And you can see that the trap size increases with decreasing clock phase time. And it seems to approach an asymptote as you get to really high pixel times, if you're patient enough to wait that long. So at a megapixel, we have 1,000 nanoseconds, which is 100 on this plot, to do 6 phases of shifting to get charge across. So that's just not going to work off on the right there. So we have to take a charge transfer efficiency hit as we go to faster pixel rates.
Joe, can I ask you to try and wrap up in the near future so we have time for Ashley as well? Sorry.
Yes, I am sorry. I'm wrapping up pretty quick here.
Okay.
The trap is a function of the number of pumps, and it can be linearly extrapolated, and then we can fix that up. Should that? And then I never get to this last slide, but I'm gonna try and squeeze it in. The last thing I wanted to talk about is noise, and what we're doing to minimize that. And I'm just gonna have to skip through this. This slide I showed is an output stage of a newer CCD design that we've got. Notice that there's no contact on the output gate. So no charge is transferred, allowing us to multiply sample the charge non-destructively, like you're doing on the NRG devices. And we can get to very good noise by sampling that charge rapidly, multiple times. We've made it. And this is sort of what we're seeing. And I wanted to get this in there, squeeze this in, because I think this is relevant to the community doing, trying to build the next generation of EPRV spectrographs. So this is, you're seeing individual electrons on a 5-electron flat field. And overlaid here is not a model fit, but a synthetic Poisson distribution showing you see the Poisson statistics in individual electrons. And sorry that this really feels out of place now that I'm going through it, but I'm kind of going to skip ahead for Ashley. There we go. We'll stop it there.
Okay, sorry to cut you off.
No, you didn't cut me off. I realized that I just got going too slow.
No worries. Okay, so why don't we hop over to Ashley? We'll hold questions till the end to make sure she has time to present. And so folks, feel free to put questions in the chat, or we'll come back and ask for hands once Ashley wraps up. So Ashley, go ahead.
All right. Thanks, Jen. And thanks, Joe, for the intro. I have much less deep understanding of detectors and manufacturing, et cetera. So I'm going to try to give the perspective of an EPRV or PRV instrument, specifically KPF and HISPEC, and how we went through detector characterization with Joe's help. So I'll refer to a lot of the things that he mentioned. But first, I just want to start with KPF and CCDs. I think that's what I'll mostly talk about today, and do a little bit on HISPEC at the end. But just in case you're not familiar with KPF, it's a high-resolution PRV instrument at Keck on Keck 1 telescope. So in the figure on the left here, you can see this is a Keck 1 telescope, and fiber feeds KPF, which is in the basement. It's has resolution of about 95,000. It has all of the typical calibrations that RV spectrographs have, like LFC, Etalon, and it's aiming for 30 centimeters per second systematic RV instrument precision. So here's a image of the spectrograph on the left diagram. I just want to point out that the bandpass of KPF, which covers the optical, is split into the red channel and the green channel. So we have two STA 4K by 4K detectors. And this is an image on the right of one of them. And so if you just look at the spectral format, this is what it looks like once you stitch the image together. We have 4 different amplifiers. So there's some stitching that happens, which I'll talk more about later. And there's a few traces here because the science fiber is split up into a few. And then there's a calibration trace and a sky trace. And so what we want to focus on here is this RV error budget and kind of how detectors come into play here and how it relates to all the manufacturing details that Joe talked about. And so you can see, so Sam Halverson compiled the RV error budget for KPF, and you can see that the detector effects, the red column here, sums up to about 7 centimeters per second. Of course, this is the budget, and so you have to validate this. And that was part of my role on the KPF team. And so this is quite a small contribution, but it can blow up quickly if you're not careful and you don't monitor it. So I'm going to talk about a few of the things that came up with us. First of all, I just want to point out that some of the things like CSD thermal expansion on this list are pretty well taken care of. So these numbers here, if you think about the detector changing temperature by like a millikelvin, say, these numbers aren't necessarily for KPF. I forget exactly how wide KPF's detector is. This is for HISPEC, but for a 6 centimeter wide array, just given the expansion coefficient of the material, it'll shift by about 1/4 of a nanometer over the width of it in a 1 millikelvin temperature shift. We've gotten pretty good at thermal loops, control loops, and so KPF detectors are stabilized to 1.3 millikelvin, and this all corresponds to about 1 to 2 centimeters per second effect before calibrating. For readout thermal change, you might know that when you're not reading out your detector, so if this is our CCD with the image area in gray, that's shifting charge to the serial register over here, this column, which then 1 by 1 shifts a pixel to the amplifier for reading out the signal. You might know that when you're not reading out, when you're just idling, or when you're not integrating, you're just idling, or if you're reading out, you're constantly shifting the charge because you don't want to accumulate dark current in your pixel wells. But when you're integrating, so that creates heat, and when you're integrating, you're just sitting there still and collecting charge. In a long integration time, the temperature can really drop. And this was done in Colin Blake's paper in 2019, where they found a way to dither the pixels, and actually Joe's on this paper. So when you're integrating, instead of just letting it sit idle, you actually move the charge back and forth in a single pixel. And then, so the black is the temperature transient when you're integrating with no dithering, and the red is with dithering. You can see that it really improves the temperature stability. And so KPF implements this, and we see a similar improvement. So going to charge transfer efficiency, which Joe talked about, just want to remind everyone what exactly it is. So it's how efficiently the charge gets transferred between pixels as it's getting shifted to the amplifier. And so if this is your serial register here on the right, where you're shifting charge into, and as you move a single charge, say, to the amplifier, a fraction of the charge is going to get left behind because this is an imperfect process, because all these traps and other effects that Joe mentioned. And so once you get to reading this pixel and the charge in it, you have all this leftover charge. And so this is what Joe showed, is that if you look at the overscan edge, so the overscan is when you can keep transferring charge, that keep transferring charge into your amplifier from where you've already passed the image space. So now you're just clocking and reading in excess charge that was left over in the serial register. You'll see that there's a lot of there, is this measurable amount of charge that's left over, which is being shown here. And it depends on the flux in this that you started out with in your image area. So what this does to your spectrum is you can imagine that this tail here affects your absorption lines. And so if the black line or the orange line is your normal stellar spectral feature that has a centroid, then if you have bad CTE, then you'll get an extended tail to your PSF, and that will change the line center. And because the real impact is because it changes with the signal to noise ratio. And so the shift won't be as much, say, if the charge isn't, if your signal noise ratio changes. And so for KPF, we, Joe measured it and found that we were in spec. We measured at Caltech and found out we were in spec. And then Ryan Rubenzahl, who's leading the SoCal efforts, found that when he changed the SNR of the SoCal exposures, the solar spectra, the RV there, he found like an RV offset. And at some point when we moved the detectors to Keck, we had also checked, I'm going to skip over this. We had also checked the extended pixel edge response, so this overscan region, and we found that the one quadrant of the green detector was wildly out of spec now. And so KPF has 4 amplifiers for each of its detectors. For the red detector, we actually only used 2 of them because we knew that one of the serial registers in amplifier 3 had a charge trap in it. So we avoided this to not incur bad CTE in that quadrant. But it looked like now the KPF top left green amplifier was experiencing some really high CTE. And so if you mask that quadrant, this is a figure by Sam Halverson with data from Ryan. If you mask the top left quadrant, the bad quadrant, then all of a sudden this correlation between RV and exposure time, so these are at different exposure lengths. And for AMP1, it's really, really bad. That's the bad amplifier. If the whole frame averaged together, it's still bad. And then if you mask that, the problem goes away. And so the way that we fixed this was simply switching the green to 2 amplifier mode, which actually, I say simply, but because I had to do the ACF file changes, it was a little challenging for me, but we did it with Joe's help. And now there's no SNR dependence. We don't think that the problem was due to a charge trap, by the way. The effect was the CTE and the extended pixel edge response kind of looks different than it would have if it were a charge trap. It's likely there's some electronic issue that happened upon moving to Keck. But the solution actually is quite nice because of how we optimize a faster readout mode for 2 amplifier, and actually now the readout times of the 2 detectors match. So going to a effect that was not originally on the list is detector fringing. So Joe mentioned this earlier and explained it quite nicely, but it's due to the photons interfering from within the silicon layer, and this causes detector fringing. It depends on the QE, the thickness of the silicon, the wavelength of light. And just to show this GIF again, what Joe didn't mention were the amplitudes of the fringing and our requirement. So our requirement was 1% and the amplitudes are much, much higher. And so we had to kind of think about how we were going to correct this. in the data. One thing that we tried, because Roger Smith has a collaborator, Philip Rosnet, who actually has been trying to model detector fringing. And if you use the fringe spectrum and the frequency of how the fringes change in wavelength, you can derive a thickness map of the KPF detector. And actually, if you take a flat ratio, because of how charge diffusion changes, the depth of a photon, how deep into the silicon layer that the photon absorbs depends on the wavelength of the light. If you take the ratio of two flat fields at two different wavelengths, you actually get a proxy for a thickness map. So actually, Philippe used this as the input to his fringing model. And oh no, it's not playing. Well, this is a fringe map that that he actually just simulated. So qualitatively, it's very similar, but we can't actually use this to correct the fringing because of how complex the situation. Even if he tried to fit his model to the data itself, to this fringing map, he still wouldn't recreate it perfectly. So you're left with using flat fields. So you can see in this these 1D spectra of KPF spectra of the red detector where the fringing is an issue. At the bottom, it kind of kicks on at around 700 or nanometers. And so daily flat fields really improve this, but there's more improvements needed at the 1 meter per second level. So let's see, time. Okay. So related to Joe's experiment with the where he projected interference pattern on the detector and shifted around, what we did with KPF, and at Caltech we have this spot projector lab that will image a mask onto the detector. So the optics are set up as shown on the left. What you do is you get a mask with a bunch of pinholes in it, and that are very precisely positioned, and you can shift these spots on your detector to scan either subpixel sized spots or larger, depending on the F number you choose for the setup, and at different wavelengths. And this way you can characterize a lot of things of the detector. And so hopefully this one plays. Yeah, so this is an image of actual spots moving across the KPF detector. This is a part of the mask that where the pinholes are slightly bigger, so you can identify exactly where you are between frames, which is why there's a little F here. So these spots are, because you have so many spots, you can get the bulk position shift of the mask and very precisely know the offsets of the spots. And so this kind of relates back to the pixel center offsets, pixel inhomogeneities, and also the brighter fatter effect, which I don't have time to go over. But by changing the intensity of the spots, you can gauge the brighter fatter effect. You can also probe charge diffusion. And so don't have a ton of time, but this image on the right here is showing a reconstruction of one of those spot PSFs. So because the spots are subpixel, or when the spots are subpixel, you want to be able to reconstruct the actual PSF so that you can then use it to do measurements like the intrapixel QE variations. And so to do that, you dither the spots a bunch and then reconstruct the PSF. So that's been done, and the spot tracking has been done for all the data that we took. But there's some analysis to go. And the goal, I would say, is to do something like in this paper in Mahara et al. 2018, where you can actually take this PSF, take your data, and try and reconstruct probably coarser than this, but a subpixel response map. Okay, so I have 5 minutes left. I'll try to cover near infrared just really briefly, just give an overview so there's some time for questions. But another project that I'm working on is HISPEC, and HISPEC is like KPF, but it's in the near infrared and it's diffraction limited and it's on Keck 2. So this is diffraction limited spectrographs are ideal for large telescopes because it keeps the size manageable. But to do this, you have to efficiently couple into single mode fibers. So you need AO, which is more doable in the near infrared. And HISPEC in particular is also split up into two channels, a red and a blue, but in the YJ and HK bands. And it has two H4RG detectors, and we're really hoping to get two 10s. And it has multiple science cases, unlike KPF. Of course, KPF can do other science than PRV, but a lot of the science drivers for HISPEC are not PRV, but PRV is really driving the requirements, and we're trying to aim for sub-meter per second precisions. So the difference between CMOS and CCDs are quite stark. So CCDs, you are transferring charge between the pixels and then reading out in one amplifier. But in the CMOS, which is like an H4RG, each pixel itself is its own circuit and you're really just changing the probes and where you probe to measure the charge. And you're not doing it all at the same time. You have to scan. And so there's drifts and read noise variations that can happen that don't happen in a CCD. This is our HISPEC RV error budget. For the detector section, you can immediately see that the budget for the detector RV error is a lot higher. It's 20 versus 7 for KPF, and that's because near-infrared detector is much more difficult. And in particular, persistence and read noise and interpixel capacitance, which I won't have time to talk about, are problematic. So persistence is where your charge gets left on, you take an image that's really bright, and then the next image you see some of that charge still. And this is, of course, bad in a spectrum because it's like your spectrum has a little ghost on it, and it might change with our shifts and cause an RV bias as a function or across epochs. And we're hoping with the H4RG 10s, so a lot of work has been done by the WFIRST mission to really improve the, particularly the persistence of these detectors down to around the like 0.1% level. And on the right, I'm showing simulations where if you put in like a ghost, like a persistent ghost on top of a M dwarf or G dwarf, different spectral types, what the RV error is. And you're getting around the 10 centimeters per second level at a 1% contrast of your persistent ghost. And read noise is my second to last slide. There's a lot of read noise you think of being not a systematic error, but in H4RGs, it becomes more complicated. And so we kind of group all of these weird effects that can happen that are shown on the left. And if you don't do reference sampling and correction of these, then you can have a very significant RV error term as simulated in the Spectre et al. Paper in 2019. And so we're kind of close to the top of the hour, so I'll just leave these takeaways up and hopefully there's time for a couple questions.
Yeah, thank you very much to both of our speakers for excellent talks. Folks, feel free to use the little clapping hands emoji to show appreciation. And if there are questions online, please use the raise hand feature so that I'll see it pop up in the chat and we will start calling on people. One hand up, which is not. Oh, Sam, go right ahead.
Thank you both for those overviews. That was awesome. Question for Joe, mostly, probably, maybe. So I think the stability of the fringing we've noticed on flat field exposures is quite good on KPF, which makes sense. I think, at the sort of sub-meter per second level, if we start thinking about the fringe pattern as kind of a linear combination of all these different emelons, right, which are from different wavelengths, different incident angles, et cetera, it does change enough, especially as the stellar spectrum moves around with the barycentric velocity, that we really can't apply the very, very nicely modeled fringe pattern from flats, or even if we model it for the same star a different day, and get very, very flat photon limited residuals. So I think there's still utility in pushing towards, squashing this further at the kind of manufacturing level. And I kind of wanted to ask about, are there more paths ahead for doing this?
And so the principal path, I think, or the principal path towards that would be to try and reduce what's causing the etalon effect. And so I think anything that makes a bad etalon is kind of what we're trying to do to the CCD. So when people have solved this, it's basically been through roughening up what's considered the front side, which is that middle layer at the end of the CCD. Because you don't have to change much, right? A few nanometers will make the fringe in theory go away. Also, thicker devices would make it go away, or it reduces. I'm curious to see how it's affected by really red light on really thick devices, because we haven't done much testing with that. But I think if you roughen that front side layer, is probably our best path forward towards reducing the fringing effect.
And I guess as a quick, are there plans for experimenting with this at STA?
Yes, but it's not high on our list. We've got a lot of other things going on. So because it's been done at other places and worked and other places, we know that there's a path forward. We just need to allow time and sort of fabricate. We have to split lots and fabricate devices to experiment with that and see if we can avoid breaking things when we do that.
Okay, other questions from folks online? Andreas, go right ahead.
Yeah, thanks a lot. Great talks. I wanted to ask about the CTI effect. So from what you said, it should be much stronger in the serial register. So that means you should, in principle, align that with the cross dispersion direction, so that the effect on the RV is not quite as large. Is that kind of predictable when you design the instrument, or are there, say, device-to-device variations that in some cases you may be doing the wrong thing?
Ashley's probably better qualified to answer.
I was just going to say that if you orient the spectral orders in the direction of the parallels, then you run the risk of, if you have a bad column, then you're going to wipe out like a whole order or ruin a whole order. So I think that's why typically we orient the orders the way that we do. But yeah, Joe, if any others have things to add.
Yeah, that's correct. But to address your predictability question, the CTE is not, it's affected by traps that we can't predict. And we certainly select the ones with the best CTE. And but Ashley's absolutely right. It's in almost all cases, you want your spectral orders to be where bad columns wipe out only single wavelengths rather than entire orders.
Yeah, that's what one normally does. Of course, it depends a little bit on the exact optical layout, on how many rows you spread your light and so on, whether you can still use an order even if it's blocked. But yeah.
It's also worth pointing out that the serial CTE is better than 6.9s in a lot of cases. So it's pretty good unless something's gone wrong.
Okay, and Andy St. Georgie, go right ahead.
When you say roughening up that surface, is that what E2V is advertising as defringing?
I don't know for sure, but that's our guess. They
Okay.
don't really communicate any details.
I imagine you guys don't go out for brewskis on Fridays. But...
We actually have we do talk to them, and we have talked about using their fab for some of our devices. It's not a bad relationship in any sense, and they have come and visited us, and we actually have a brewery next door and have gone out for brewskis. But they share very little in terms of they consider sort of everything proprietary, even though this stuff's been done for 30 years, so 40 years. So it's not. So it's that's my guess, is that that their defringing is roughing up the surface in some way.
Okay, we're a little bit past the top of the hour. Any last burning questions for Joe or Ashley? Okay, if not, let's thank our speakers again. Thank you both so much for calling in and presenting. As a reminder, we will not be having a colloquium in December because it would overlap with the Christmas holiday. Instead, we'll be having the EPRV survey design meeting on the 18th. Again, you'll get an email reminder about that when I send out the recording of Joe and Ashley's presentations. So thank you all so much for calling in and being lovely participants, and I will catch you all in a few weeks.
Thanks, Jen.
And thanks, folks.